the work of the PROLOG inference engine, how this search engine is working. And today we are going to go in more detail in that process. So we have that search engine is always going top down through facts, left right to satisfaction of goals, and then uses pattern matching of facts and expressions and instantiates variables during that process. And then whenever it fails, it is backtracking to previous goal. So for example, if go to this database of facts, so fact about brother, 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 sister, sister, etc. Through this database of facts, machine is always going to go top down. First this, second this, third this, fourth this, etc. Always top down. And when it comes to rules, it is going to go left to right. So if we have a rule, with variables x and y, then this rule is satisfied if we can satisfy goal 1 and goal 2 and goal 3. So to satisfy this goal with variables x and y, we have to satisfy these 3 goals. Now, what we can do, let me tell you immediately, is to replace these x and y with constants, and then to try to see whether these constants that we put here can satisfy goal 1, goal 2, and goal 3. For example, you put here number 1, here you put number 1. Can you satisfy goal 1 with number 1? Yes or no? If you cannot, then you fail and it is over. If you can, then you try to satisfy goal 2 with number 1. If you fail, it is over. If you can, go to goal 3. Try to satisfy goal 3 with 1, 1. If you can, give the result yes, it is satisfied. But the most important feature of PROLOG is that x and y are neither inputs nor outputs. They are flexible. They can be inputs or outputs interchangeably. So interchangeability of inputs and outputs is a fundamental property of PROLOG that is not shared by other languages. And therefore, this is the main reason why we want to study this kind of programming, because x and y can be outputs. So if I have a rule that is written in this way, x and y are supposed to be outputs because they are not instantiated with anything. These are 2 outputs. So how to find x and how to find y? First, we are going to try to satisfy goal 1. We are going to go through the database of facts top down and satisfy goal 1 if possible. If it is not possible, then we fail and that's it. Now, if we satisfy goal 1, we have the value of x that is instantiated at the moment of satisfaction. For example, you can say brother of John is x, okay? And now this x is either brother of John or not brother of John. So if you find somebody who is brother of John, for example, George, then you have x is George, and this is what is instantiated variable. And then after you satisfy first goal, you have to satisfy the second. So this end is telling you we go to second goal. We satisfy the second goal, y, and again go through database top down and find this value of y. Now, at this moment, we have instantiated x and instantiated y. So these are 2 values that are given. Now we go to goal 3, and we have x and y that is already instantiated. And we try to satisfy goal 3 with this x and y. There are 2 possibilities. We succeed. In that case, you are going to get as the results this x and y. The other possibility is that we fail. If we fail, then the answer will not be no. But if we fail with this x and y, then PROLOG will go back to previous goal, this goal 2, and we'll try to satisfy goal 2 with another y. So practically, PROLOG will try to satisfy this goal 2 with another y, And when this other y is satisfied, then we'll go with other combination of x and y to see whether it can satisfy goal 3. Or if this is not possible, we'll go back to goal 1 and we'll try to find another value of x. And then with that value of x, find another value of y. And then with this new combination of x and y, try to satisfy x and y of goal 3. And if this is satisfied, then it is going to give me x is something, y is something, the result of that. So we have that when we satisfy these 3 goals, then we get the results x and y. And in this process, we are going to backtrack to previous goals if we fail to satisfy some of goals in the sequence. So this rule is satisfied if goals are satisfied, and they are satisfied left to right. So first goal 1, then goal 2, and then goal 3. Okay? Any question about this? We'll see an example. So going back to our family that we used to study in the previous case, we have that brothers are John Mike, John Peter, John George, and then sister of John is Mary, sister of John is Anne. And then John drives Ford Mustang, Mary drives Toyota Camry, Peter drives Honda, and drives Ford Focus. Now, one question that we can ask, who is the sister of John who drives a Toyota? So is there a sister of John who drives a Toyota? So John has a sister, Mary, and sister Anne. And Mary indeed drives Toyota. Anne is driving another car. So there is the solution that sister of John is Mary, and Mary drives Toyota. So the question is how to ask that question. And Mary drives Toyota Camry. Okay. So if I want to ask that question, I'm going to say that driver is S. If this S is sister of John, so I'm going to satisfy first goal that sister of John must be this S. So S is sister. And then when we instantiate this sister, we go to satisfy drives this sister Toyota something. So what is S? S is an instantiated variable. What is Toyota? This is a symbolic constant. So this is not a variable. And then here comes Camry. Now, Camry is something that we can instantiate by putting here M, which is model of Toyota. Camry is one of models of Toyota. So what we could do is to put here a variable that will be instantiated. If this variable is instantiated, then PROLOG will do the same thing what all programming language processors are doing. So language processors are looking at variables and asking who is using that variable. So imagine that you have Java or C++ program or C program, and at the end of this program, as the last statement, you write integer n equals 1. Integer n equals 1. Is this correct? Yes, of course. You say create an object that is integer, call it n, and instantiate the value of that as 1. And after that, the program terminates. So this is certainly not wrong. However, what is going to be done by compiler? Compiler will go there, will create that object and say, hey, who is using this object? Nobody is using. There is no need for that object. Then each optimizing compiler will simply kick out that piece of code and will never create this X because X is not used by anybody, and program will work correctly with or without this n equals 1. So we'll eliminate something that is called a singleton variable, a variable that is instantiated but never used. Now, In the case of PROLOG, if you do something like that, put here M, C++ will not complain, but PROLOG will complain because it is going to say you instantiate a variable that is not used in this search. So most likely you have a typo. That means if you have to put here, for example, family search and put here grandfather with, say, capital G. If you put grandfather, and if you have a typo in typing, so it is not grandfather with D, but with T, for example. And then this is most likely a typing error. So PROLOG will say you are not going to define a variable that you are never going to use because you most likely make a typo, because otherwise you don't need it. So it is going to give you error message and say this is a singleton variable. So we have here a concept called anonymous variable. An anonymous variable is a variable that has no name. It is anonymous in the sense that it is variable that has no name, and you tell the PROLOG language processor that there is going to be an object here, but nobody will use that object. So this is going to be object that is not going to be used. Therefore, this rule is satisfied like this. You say, give me this S, so that S is sister of John. And then it is going to put here Mary and then. And then this S, which is now instantiated to, for example, Mary, should drive Toyota. But we don't care which Toyota. Any Toyota would be okay. So this sister can have two different models of Toyota, and that would be okay. So also, so drives this sister, Toyota, yes, you're satisfied. Is this Camry or Corolla or whatever else? We don't care. This can be irrelevant. So I have here the rule that has the driver is S if driver S is sister of John and drives Toyota. So this is the rule to find this driver. Now, when I use this rule and say, give me this driver, how will this work? I say driver is somebody who has a name, give me that name. And the name will be Mary. Why? Because if we go here, you first look top down to find sister of John. So this is brother fails, brother fails, brother fails. Sister, yes, sister of John is Mary. So put S equals Mary and put pointer here. This is pointer for sister, okay? And then go to rule number 2. Rule number 2 is drives Mary Toyota. So now you are looking for drives Mary Toyota, whatever Toyota. Go again here and drives. There is no drives here, but drive starts here. Drives John, this is not Mary. Drives Mary, here we go. Drives Mary Toyota. It matches drives Mary Toyota. Camry is not important, and the pointer comes here. So pointer for sister was here after Mary, and pointer for Toyota, for drives is here. So practically this search created 2 pointers. One is here at sister Mary, and the other pointer is Mary Toyota, drives here. And then we are going to have the result. Name equals Mary. And this is how the result is created. Now, there are 2 possibilities. Either you press return, in which case you say, I'm satisfied with this, I have no other questions. The other possibility is to put semicolon and to say, now give me more drivers who are sister of John and drive Toyota. And of course, there is nobody in that list more, and the result will be no. There is no possibility for that. On the other hand, nobody tells you that this driver S must be the output of the search. S can be also input if you want. So what you can say is an driver who is sister of John and drives Toyota. And then how is this going to work? Well, it is going to go first looking whether N is sister of John. So here we have brother, 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 brother. We skip that. Come to sister. Sister of John is Mary. This fails. Sister of John is N. Yes, this succeeds. So we succeeded with sister of John is N. Put here the pointer and then go to satisfy whether N drives Toyota. So we go here, skip brother, brother, skip sister, sister. Drives N Toyota. So drives N fails here. Drives N fails here. Drives Peter fails here. Drives N succeeds. And then comes to comparing Ford and Toyota. They are different. Therefore fails here. And the answer is going to be no. So the answer is N driver? No. Because it searched according to this rule that it is sister and drives a car, but found no matching, and the answer is no. Then you can ask, is driver Mary? And for the same reason like in previous searches, you're going to get yes, because you can satisfy that Mary is sister of John, and you can satisfy that Mary has Toyota car, and therefore the answer will be yes. Or you can say, these are not going to be inputs, but output, so find me somebody who is driving Toyota. Name is Mary, so you get this as a result. Now, interchangeability of inputs and outputs is a unique property that exists in PROLOG. Therefore, this search mechanism that is searching for solutions, going through facts and rules, and satisfying both of them, this is something that is unique to PROLOG. Other languages define always whether something is input or output. However, in PROLOG, you can be either input or output, or combined inputs and outputs any way you want. And this opens the whole new world of solutions, and this is why we study this programming paradigm, because it is a paradigm based on pattern matching and searching for solutions. And this is something that is completely new, unique to this problem solving, and can give you the possibility to solve many very complex problems in a very simple way. You're going to see that. Now, is there any question about this, what we studied so far? If you have any question, just unmute your microphone and ask the question directly. Or you can raise your hand. I'll see that somewhere on the screen, and then we'll stop anyhow. So is this clear so far? Okay. If it is clear, we continue. There are also disjunctive queries. So in all these queries so far, we have a conjunctive query. So driver is S if S is sister of John, and this comma is and. So you have to satisfy this goal, and you have to satisfy this next goal. And if you have multiple goals, all of them have to be satisfied. So the driver is going to be somebody who satisfies first goal and second goal and third goal and whatever is the number of them. However, we can also have the situation where we want to have disjunctive query. So you can say, let us make the rule for siblings. So P and S are going to be siblings in two cases. Let's go first here at the bottom. The first case is if you have that sibling of person P is S, if this S is brother of P. This is the first possibility to satisfy this sibling rule. The other possibility is that sibling of person P is S, if S is sister of this person P. So you can be either brother or sister. Okay. So these are rules like one that you have to do in your homework. Homework has this family, and you can have brothers, sisters, and there are siblings that you have to define, etc. So who is the sibling of person P? You can say sibling is brother or sibling is sister. Pay attention that if you have multiple rules like this one, sibling is brother, sibling is sister. Therefore, there is the or connectivity between this first rule and second rule, because after you satisfy or fail to satisfy first rule, you are going to satisfy maybe the second rule. So you either satisfy first or satisfy second, you are going to get your sibling. Therefore, this is brother or sister. So you have sibling if you have brother or you have sister. Now this or can be written using semicolon. Therefore, sibling of person P is S if this S is brother or if this S is sister of person P. So there are two possible notation. One is this one here, the other is this one here. Most frequently, you have that PROLOG programs have this notation, that you simply write that 2 times, because you see that these are possibilities that are satisfied, and you can satisfy them in 2 different ways. Of course, you can also write in this way, but then it is not clearly visible when you fail and when you put the pointer, because you can have pointer here between these 2 things. So here is the pointer at the end of first or end of second, whichever you satisfy. Therefore, this is more frequent in PROLOG programs than this OR, but they are equivalent. So there are AND queries and OR queries. So if you have a query that has AND, this is usually called conjunctive query, because AND is the logic conjunction, it is simultaneity, and OR is logic disjunction, that means substitutability. You can substitute brother for sister, and it is going to work the same way. Now, if we have to satisfy a sequence of goals, goals are satisfied left to right, first, second, third, etc. So for each satisfied goal, there will be a pointer in database that will tell you exactly where you satisfy that goal. And pointer will be, of course, not visible to programmer, but search engine will put a pointer there. For what reason? To be able to continue search from that position that was already reached in previous search. So if you can satisfy the goal, you put a pointer there and continue left, right, and top down. If a goal is not satisfied, then you have to perform backtrack. Search engine will be backtrack. So it returns to previous goal and continues search from the previous pointer position. So that's why these pointers are extremely important, and that is the basic thing that has to be implemented in the search engine. If the rule cannot be satisfied, and this is very frequently the case, then the search engine will tell you, no, I was not able to prove that rule, or will tell you false. This is not true. Okay. So let us return to our previous example of friends. Friends are X and Y if X likes wine and Y likes wine. So we have here X and Y that are variables. We have here if X likes wine, Y likes wine. Now, we focus on this wine. Wine is a constant. It is a symbolic constant. It is an atom. And wine is here and wine is here. So X must be wine and Y must be a person who likes the same wine. But you can say also, friends are people who are not just having wine in common, but something else. So you can say friends are two people if they like the same thing. So you can modify rule and say friends are X and Y if X likes something and likes Y the same thing. So this is the rule that says two people are friends if they like the same thing. You don't know what is this S. So PROLOG will first find this S that X likes. And then this S is going to be instantiated with Y. And then we'll go to the next goal, like this one here, and trying to find somebody who likes the same thing, wine. So now wine is instantiated from here, but Y is the variable that has to match something. And then if you find that X and Y match the same thing, then you're going to get X and Y. Now, you are going to get the result, what is X, what is Y. So if you say friends are X and Y, it is going to tell you who is X, who is Y. However, the first thing that I want to mention here, you will never know what they have in common. So maybe somebody likes tennis and the other person also likes tennis, and you are going to get that they are friends, but you are not going to know what is common between them, this S. That's the first comment. Second comment is make clear understanding that this S is not a singleton variable. Singleton variable is variable that is not used. However, this S must be instantiated before you go to this likes YS. So practically, this is instantiated with wine, and then you go to check whether there is somebody who likes wine. And therefore, S is going to be used. So this S that is instantiated here will propagate through all other rules that have S in it. So this is not a singleton variable. That's the first thing. The second thing that you see here is that unfortunately, these X and Y will be the same. Because if you go through database of facts, you don't say that these X and Y must be different people. So if you go and check for everything that exists in database, you're going to satisfy this X S with Yozo wine. And then when you have here wine that is fixed, you go from the top down and you again find Yozo wine. So you say X is Yozo, Y is Yozo. And this is the solution that you have here, Yozo, Yozo. And then if you give request to continue search from the position that was found so far, then you are going to get Yozo Iceman. And Yozo Iceman is going to be second solution. Then you say, okay, give me more solutions. Then the search continues from that position and you get Iceman Yozo. This is the third solution. And then you say, give me more. Then you are going to get Iceman, Iceman. So you have, again, this trivial solution. And after that, you say, give me more. It will tell you, no, there are no more solutions. So this is the case when we want to get all friends in this case. And these friends are Yozo, 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 Iceman, Iceman, Yozo, and Iceman, Iceman. So you can say, hey, these are trivial solutions. I don't want this. I want to write the program. Gives me two people, two different people who like the same thing. They are friends. Of course, this is easy to do. You just have to say that this have to be two different people. So here is the rule. Friends are X and Y. If X likes something and Y likes the same thing, and third goal, X must be different from Y. So different is written not equal, not is this backslash equal here. So X and Y must be different. So when you create this solution, Yozo, you are going to fail here. And if you fail, you have, so if X is Yozo and S is Y, and here you come to Y is Yozo, S is Y. And you come here, Yozo different from Yozo, you fail here. Since you fail, PROLOG will backtrack back to these likes, to previous goal, and will say, hey, I have to satisfy this with somebody else. And then we'll continue from here and we'll find that Iceman likes wine as well. And now we'll have X is Yozo, Y is Iceman. We'll come here and say, Yozo is different from Iceman. Yes. So when you satisfy this and this and this, these three goals, then you have X and Y that satisfied all three goals, and you give the user the result. X is Yozo, Y is Iceman. And then you wait to see what is going to be the next thing. And the next thing, if you put here return, then we'll give you a prompt and tell you, okay, give me the next solution. Or if you say continue search from this position, continue search from this position, it is going to go from this X is Yozo and Y is Iceman. And then we'll find that after Iceman there is nobody here, we'll backtrack here, we'll put here X is Iceman. And then we'll go with search from the beginning. And from the beginning, we found that Y is Yozo. And then this is wine, and we'll say, aha, Iceman Yozo is the third solution. And finally, when you put semicolon, we'll find Iceman and Iceman. And fail here, give you this fourth solution. And if you have this rule, it is going to fail. So now I have two questions for you. The first question is, in human reasoning, you can say friends are X and Y. If X and Y are different people and they like the same thing. So in human reasoning, you could take this X different from Y and put this at the very beginning here. So what do you think? Would it be possible to put this X different from Y as the first goal here? So friends are X and Y. If X and Y are different and X likes something and Y likes something. Do you see any reason why this is okay or not okay? The answer to that question is that this is not okay. And explanation is this one. If you put X is different from Y, which is perfectly okay in human reasoning at the beginning, then since you go left to right, you have that X is a noun value and Y is a noun value. These are two uninstantiated variables. So since you don't know their values, you cannot check are they the same or not. So for this relationship to be tested, to be checked, it is indispensable that both X and Y are instantiated. And they are instantiated from the search mechanism, and search mechanism is based on likes predicate. So you must first put likes X, S, and now you instantiate X. Then you go with likes Y, S, and then instantiate Y. And then when you satisfy first and second goal, you instantiate X, you instantiate Y. And now you come with X and Y that have specific values. So you can now check whether these values are same or different. Therefore, do they match or not match? And now is possible to have answer here, yes or no. So this is the reason why this cannot come at the beginning. Now the next question, can somebody tell me, is it possible to permute these likes xs and ys? So to put these likes y first and likes x second. Can I do this permutation? And then x different from y is the last one. Would that work or not?
Yes.
Bravo, bravo. Yes, I completely agree. Why? Because you can instantiate first y, then instantiate x. You are going to have that all of them are going to find what is the common s. So is this s found from x, from y is the same thing. You have to satisfy this in any order. So this permutation is okay. But let me ask you the third question. If I put this x different of y here in the middle between likes x and likes y, would that work or not?
No.
Bravo, bravo. No, for what reason?
Y hasn't been instantiated at that point.
Of course, at that point, y has not been instantiated, and therefore you are checking one variable that is instantiated with one noun variable. There is a big difference between this relationship and this predicate relationship. Predicate relationship is generating the values of x and y by going through the database of facts and finding matching. So this likes is instantiating y and s. This here is a passive test of sameness of already instantiated variable. This is not a predicate that generates new values from database. So all these relationships, equal, not equal, whatever you put, has to be done with instantiated variables. You cannot do that with those that are not instantiated. This is not going to instantiate variables. Variables are instantiated from predicates and from searching the database of facts. So that is why you correctly decided that this is not going to work here. So first has to come one of these likes, and then after that comes this here. So if we have this kind of rule, then we eliminate Yozo and Eisman. This solution will not occur anymore. Now, what you can do in this case is three things. One is to ask what is x and what is y in this function friends. So this is extremely important. Both x and y are outputs. So I get outputs xy, 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 xy. However, I can also use these as inputs. So I can say inputs are Yozo and Eisman. Go through this database of facts and rules and tell me, can you satisfy this rule with Yozo Eisman? Yes or no? And then PROLOG is doing all this search and say, yes, this holds. So in this case, Yozo is input, Eisman is input. Okay. And the answer is either yes or no. Either you can prove that or you cannot prove that. Now, you can also do combinations. You can say, who is a friend of Yozo? And you say, friend of Yozo is X. So go through this database of facts and rules and try to satisfy these friends of Yozo is X with some X. And then what you are going to get as the result, X is Eisman. So Eisman is satisfying that friends are Yozo Eisman. Okay, now you say, give me more friends. Who else is friend of Yozo in this database? And the answer will be no. Cannot find more solutions. So in this database, it is not possible to find anything else except Eisman. And that is this no that is generated in this query. Now, to summarize all what we did so far, let me start with these likes Yozo wine, likes Eisman wine. So these are two facts. And then friends are X and Y. If X likes wine, Y likes wine. So in this case, wine is constant. And we have these three lines of code. And when you say, give me friends, you are going to get Jozo, 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 Iceman, Iceman, Jozo, and Iceman, Iceman. Of course, this is not a good solution. And we want to do modifications. The first modification, we want to generalize this from wine to something else. So we put here variable W and say, I don't care what they have in common. Maybe they both like soccer and go to soccer matches together. So they are friends because they like something, but I don't care what is that something. Now, if you want to know what they have in common, what would be necessary to do in order to know what is this W? There are two possibilities. The first is to put this W here in the list of variables, X, Y, comma, W. Then you would get the results, Jozo, Iceman, and W equals wine. So you can say Jozo and Iceman are friends because both of them like wine. That would be the possibility number one. So if you put this W as one of interesting variables, whatever is listed here will be reported to the user, same as this X and Y. There's a third possibilities that we didn't study so far, to say likes X something, likes Y something, put here comma, and say write W. Write W means you know this variable, tell me what they have in common. And then you write wine. And then you say wine, and then you have Jozo, Iceman, Y, Iceman, Jozo, etc. You can do it that way also. Now you can eliminate duplicates. The first thing that we usually do, we eliminate duplicates, and therefore you say friends are X and Y. If X likes something, Y likes the same thing, and X is different from Y. So these are two different people. X and Y, two different people, are friends if they like the same thing. Again, you don't know what is W. So if you have this kind of rule, then you are going to get friends are Jozo, Iceman, and Iceman, Jozo. You get this permutation because all permutation do exist. You can eliminate permutations. You will see a little later how to do that. But at this moment, we have that we get these two solutions, and this is the same thing, but just permutation of it. And this is generated by this rule that friends are X and Y. If X likes something, and Y likes the same thing, and X is different from Y, if X is not equal to Y. So this brings us to very important topic of PROLOG search mechanism that we have seen in these previous examples. So let us now show that mechanism from the beginning to the end. So what we have here is database of facts. This is this line of rectangles here. Database of facts is practically what we have here. Fact is that brother of John is Mike, brother, sister, drives. These are all database of facts. And you go through this database of facts top down, search engine is going top down and trying to match things with database of facts. So that's the first thing. Then we have we have goals. Goal 1, goal 2, goal 3. So if you have a rule consists of several goals. So what is done first? For example, you are looking for this sister of John who drives Toyota car. So you go first from the top down and try to find sister. So brother, no match. And here is sister of John is Mary. And then you instantiate this Mary and put pointer here that the match was here. So you have here sister is Mary. After that, you go to the other goal. You go to the other goal, and the other goal can be that this sister drives Toyota. So you go here, drive, 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 fail, 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 until you find the match for goal number 2. Put pointer here to goal number 2, and then go to the next goal, goal number 3. Again, go through the database of facts from the beginning down, from top down, and then no match, no match, and then you find match, and when you found match, put pointer there, that match was found. Then you have these 3 matches, and you report the result. Now, if you give this result to the user can be either satisfied or asking for more solutions. There is no third possibility. So if the user is satisfied, user will press return, will use these results, and will give another query. If the user is not satisfied with that solution only, it is going to enter semicolon. Semicolon means continue search. Continue search from this point. So what's going to happen now? You have these 3 pointers, and you are going to continue search from this matching point to find next matching point. For example, this sister, whose name is Mary, might have 2 Toyota cars, one Camry and another Corolla, for example. And then you are going to continue search from this match point. So you go down, no match, no match, no match. If there is match, you are going to stop there, put pointer and say, here is the other solution. Or what can happen most frequently is that you reach the end of database of facts without another match. And then what happens? When you come here, you failed. So the only way to continue this search is to go back to goal 2. Well, this movement from goal 3 to goal 2 is called backtracking. So backtracking is going back in the sequence of goals and trying to satisfy goal 2 from the pointer position in database of facts. So we had this pointer position that we generated before. We failed to find this match here, second one. We go back to goal 2, and now we have to check matches from the beginning. And so, for example, you are finding match here at position number 2. Okay, so if you have a match here, or sorry, you had match before at position number 2, so you continue down until you find another position where you have match. And for example, you go down, no match, and find match here. So you don't touch the first one. First one is fixed. Second one is now having this second solution here. And after that, you have this match and go to goal 3. Goal 3 is checked from the beginning. No match, and here you find match. Put the pointer here. You have these 3 pointers. You generated the next solution. And this next solution is given to the user. And then the user can say, okay, give me more solutions, or can be satisfied. If the user wants more solutions, then you are going to go up to the end of these facts. And if you fail, you backtrack to goal 2. You are going to continue search from goal 2 from this position down, and most likely we fail here as well. So after you fail here, you cannot continue with goal 3. You have to backtrack from goal 2 to goal 1. So now you backtrack to goal 1 and say, okay, at the beginning we had here match. So you are looking for sister of John. So you go down and find another sister of John, maybe here. And then with that other sister, which is no longer Mary, but now is Anne, you go to goal 2 and see whether you can satisfy that with Anne. And if you can, go to goal 3, which is this goal 3. So you can have goal 1 that somebody has to be sister of John. Goal 2 can be that that sister has Toyota car. And goal 3 can be that that sister is older than 30, for example. And then you try to satisfy that it is older than 30, or that has a pet that is a cat, for example, or whatever else is the condition. So you have to satisfy many conditions, and you are going to create all combinations of them. And then after that, you either satisfy goals and give the results to user, or you say, no, I failed to satisfy these goals, so I couldn't prove that your rule is satisfied. Or you can have something else. So depending on how many goals you satisfy. Okay. Backtracking is therefore defined as the failure to find match in the set of facts. So here is failure to find match. We came to the end without match, and then we have to go back to previous goal. So the backtracking mechanism is practically going back in the search and continuing search from the position of previous successful match. So backtracking is the process of returning back to previous successful match and continuation of search from that position. So each match is registered by a pointer. So there are plenty of pointers that are set in database, in fact, so that you can continue search from that position. You don't see these pointers, but you know that they exist. And search mechanism with backtracking, this is implemented in the PROLOG search engine. So if you look, what are the basic components of the mechanism of problem solving? It is extremely simple and primitive. Pattern matching. So you try to match left-hand side and right-hand side. Pattern matching is one thing, and this systematic search, top-down and left-right. Pattern matching and search, and nothing else. So this is enough for solving all problems on this planet, and not only for solving them, but for solving them in an extremely simple way, which is not accessible to procedural and object-oriented languages like Java or C++ or whatever else. So that is the reason why we study this, because it is a paradigm that is unique, and therefore we are going to see what can be done with this paradigm. So if you have facts, you always search facts top down. Okay. When you come to rule, rule consists of several goals. For example, 4 goals. So you go left, right. You go from goal 1, 1 to goal 1, 2 to goal 1, 3 to goal 1, 4. And if you fail to continue, you must backtrack back. So this arrows going from right to left is backtracking to previous goal. So if you fail to satisfy goal 1, 4, you go back and try to satisfy goal 1, 3, starting from that position that was previously attained. And if goal 3 is failing, go back to goal 2, starting to previous pointer, and so on to goal 1. And if you completely fail to satisfy this rule 1, then you go to rule number 2, 3, 4. And you can have any number of rules that are the same. For example, this rule can have goal 2, 1, 2, 2, but the same rule can be satisfied with goal 3, 1, 3, 2, 3, 3. So again, you drop down, you try to satisfy this, you backtrack if you cannot satisfy. If backtrack doesn't help, you fail and go to try to satisfy rule with other values. So you can have different goals. So you can have rule that is satisfied in 2 different ways. It is always going to go top down and left to right. Left to right with selective backtracking. So go left to right, but return right to left when you have the backtracking process. So this gives us the possibility to see that if a rule is satisfied, then it creates results that are given to the user. And all multi-line rules are always processed left to right, and top-down until the result is generated. So if you have multi-line rule, no line can be processed unless the previous line is failing. So the point here is that if you have rules, multi-line rules, you cannot come to this rule at the bottom unless you first fail this rule here. So after you try to satisfy this rule, if there is a solution, this solution is going to be given to the user. If the user is satisfied, you will never reach this rule at the bottom. You come to this rule after you are 100% sure that you failed to satisfy previous rule. Well, after this failure, you come to the next rule. Okay. If this here is exhausted completely and all results are created, then if you ask for more, you can come down. But usually you come down simply because you failed to satisfy this rule. Now, in this process, you instantiate variables. And instantiating variables means that variable has the name and has the value of the object in memory. So this name is any name of variable, like count or x or square root or n. Now, this name is stored in a data structure that has form of table, and it is called symbol table. Symbol table is something that you are going to find in PROLOG, in Scheme, and in all languages that have dynamic typing, Ruby also. So you are going to have that symbol table will be updated during the computational process. And the language processor that has to be present during that as interpreter will maintain this symbol table. So what's going to happen here? You're going to have in symbol table first identifier or name of variable. So if you say this variable is sister, for example, or whatever, you are going to have the name of that variable here. Then the variable itself, for example, this count, will have some kind of data type. So it is going to be written inside the symbol table. This is an integer. And then the value of that integer is stored in memory. So symbol table will have object location information, which is address. And we'll have various internals that we don't care about. Some things that are also descriptors of this value that might be internally necessary. But this address is telling you that at address here, there is a number in memory. So this count is 1024. That is the value that is inside. Now, if we look at this table, there is a possibility that there is another object, like this one here, n, that takes the same position in memory. So that has the same address as this first one. Now, if this pointer is same as this pointer, then if you want to check whether count and n are the same, you don't need to go to memory. You can simply check address 1 and address 1. So if you check these addresses or pointers, then you don't need to go to memory. This is a very good news because object can be an array that has 1 million of components. So in languages like for example, C++, you are testing whether the two objects are the same, but you have to go through the content of these objects. Now, if these objects are dynamically created and stored somewhere in memory, and if you have that two identifiers are pointing at the same object, they are identical whatever is the type of object and the size of object. Can be huge, can be small. You are not going to look at that object at all. You are going simply to be satisfied by finding identity between these two addresses. Therefore, this is called that they are literally equal or pointer identical. So two objects can be pointer identical. However, you can have, for example, object X, if it is integer, that is stored in this address 2, and you can find here 1024, but addresses are different, so you have to check the values of objects in memory, not values of addresses. So you will see, for example, in Ruby, that you have this pointer identical. You can check whether two objects are the same. They're same because they share the same address. You don't look what is the object at all. And then if you want to do that, you have to have a different command that will tell you, are they the same or not? So this is the role of symbol table, and this is the role of checking objects that we have here. Is this more or less clear? I suppose that you have studied these things in operating systems or in some other class. Yes or no? I don't know.
Yes.
Most likely yes. Somewhere, is this for 413 or 5 or one of these classes that are operating system for 15, most likely. So now we come to one tricky question. How many equalities we have in programming languages, and particularly in PROLOG? We have 4 of them, and they are very, very different from each other. So there are 4 equalities that we can identify. The first one is written with equality sign, and this is pattern matching equality. So if you say that 2 things are the same, they are the same because these are matching patterns. So this is pattern matching equality. The second equality is pointer identity, written with 2 equality sign. So you have an object in memory and 2 variables that point to the same object. And you check whether their pointers are the same. So pointer identity is based on the same address symbol table. So in addition to pattern matching, we have pointer identity. The third thing is arithmetic expression equality. This is what we have in if statement in procedural languages. For example, C, C++, Java, they have if statement. And you say if expression 1 equals expression 2. If you say that, then equal, you have to put this relational operator. Then the compiler will arrange evaluation of expression 1, evaluation of expression 2, and then we'll check whether these 2 results are the same. Usually this is done by subtracting these 2 results and finding whether the result is 0. So this is arithmetic expression equality. It is not pattern matching, it is not pointer identity, it is arithmetic expressions equality. The third, and this arithmetic expression equality is identified by the fact that on the left-hand side can be any expression, on the right-hand side can be any expression. In the case of pattern matching, on the left-hand side can be any pattern, on the right-hand side can be any other pattern. In the case of pointer identity, on the left-hand side and the right-hand side should be single variables that point to something. If this is not the case, this is not going to succeed. And finally, there is assignment. Assignment is assignment like assignment in any procedural language. On the left-hand side of this assignment must be a single variable. On the right hand of this assignment has to be something that is instantiated expression. So if I say in PROLOG, n is 3, and k is n minus 1, PROLOG will instantiate n with 3, and then will compute n minus 1. Why will compute n minus 1? Because here is is. Is tells you that on the right-hand side, you have an expression that must be evaluated. On the left-hand side, you have a variable. and then k is n minus 1, we'll create 3 minus 1, 2, and we'll put k is 2. Now, you satisfy this goal here by instantiated n is 3, and here you satisfy this by instantiated k is 2. Then PROLOG comes and say you have two results, n is 3, k is 2. Okay, going left to right here. You first have to create n is 3, and then after that k is n minus 1. One thing that you will see that you cannot put here n. N is n minus 1, which is the way how we do counters in procedural languages, is not the way how this is done in PROLOG. In PROLOG, this has to be different from n. Has to be another variable that is instantiated in this way. You cannot instantiate n from this n. You have to instantiate something else. So 4 of equalities are pattern matching, pointer identity, arithmetic expression equality, and ease assignment. So let us now see all of them. Of course, we have also negation of them. So equalities and inequalities, there are 7 of them. The first is pattern matching equality, pattern matching inequality. For example, 2 people must be different. So you cannot have Iceman equals Iceman. This is going to fail. But here, Iceman equals Iceman, yes, this is going to succeed. Then, literally equal, that means that you have that the same pointer is here, same pointer is here. So you can have 2 variables that are different, and one is pointing to Iceman and the other is pointing to Iceman. You are not going to have that they are literally equal unless Iceman is unique value in the same location. If this is in different locations, it is not going to work. Arithmetic equality and inequality, and assignment. So pattern matching equality, inequality, literal equality, inequality, and arithmetic equality and inequality are 6 of them. And then assignment is number 7. So having that, we can try to see an example. If I say x equals 1, this is pattern matching. This pattern is same as pattern 1, answer is true. Is 1 arithmetically equals to 1? Yes, it is. Subtract 2 of them, you will get 0. True. Is 1 pointer identical to 1? This is a single constant that exists in memory. This is pointer identical. There is also strange possibility to compute this 1 and then check with this what is on the left-hand side. If it is the same, a PROLOG will say true. Also with is. So it is not going to assign the value, but it is going to check them and find the sameness and answer true. However, you ask whether 1 plus 1 is 3 minus 2. If these are 2 patterns, they are completely different. We have false. If we ask, are they pointer identical? Of course not. This is one expression. This is another expression. We don't have this as the same expression in memory. False. You can pattern match x with 3 minus 1. You are not going to get that this is 2. You are going to get that x is 3 minus 1, because this is pattern 3 minus 1, and x is this pattern 3 minus 1. So without computing. If you ask whether x is 3 minus 1, well, then 3 minus 1, because of this is considered arithmetic expression. It is evaluated, and then x is 2. You can also ask whether 1 plus 1 is 3 minus 1. It is false, because you cannot have an expression on the left-hand side here. It must be a single variable. When you ask arithmetically whether 1 plus 1 is 3 minus 2, you evaluate here 2, evaluate here 2, 2 is equal to 2, answer is true. So this clearly shows the difference between pattern matching, assignment, pointer identity, and arithmetic equality. These are 4 different things. Here is the case where we try to see whether x is not whether, but to assign x is 1 plus 2 plus 3 plus 4, the result is x is 10. You can also check whether x is this expression, the result will be yes. But you cannot say 1 plus 2 plus 3 plus 4 is 10, because this is not a single value. So this is going to be answered no. Same is here. You cannot instantiate 1 plus 2. This is expression. Therefore, the answer is no. But if you ask arithmetically whether 1 plus 2 is 2 plus 1, the answer will be yes. Arithmetically, they are the same. If you assign x to be 1 divided by 3, then you get x is 0, 3, 3, 3, 3, 3. Now, if you try to see whether 0, 3, 3, 3, 3, 3, plenty of them, is equal to 1 divided by 3, the answer will be no. And to understand why it is no, we have to understand that it is very difficult to fit these trees in the same bit pattern as when we divide 1 and 3. Therefore, you are not going to have this fits neither here nor here arithmetically because of differences in the last pattern. However, if you check whether arithmetically 1 divided by 3 is 1 divided by 3, yes, they are the same because when you divide them, you are going to get that the result will be whatever is pattern in memory, same on the left-hand side and the right-hand side. And also, if you consider this as constants that pattern match, they are going to pattern match, and also they are going to be equal pointer identical because these are the same constant. Now, you know that we had this result that likes Yozo-Wine and likes Weissman-Wine is giving you two solutions, Yozo-Eisman and Eisman-Yozo. Now, you can eliminate this duplicate solution by saying friends are x and y. In x likes w, y likes w, and x is different from y. And then you have cut. So this cut that we are going to study in great detail is a mechanism that is procedural. If you have goal and then you have cut and another goal, then you can go in this direction and you cannot go back. It is a procedural element in an otherwise unprocedural world. So you satisfy this goal. Cut is always satisfied. You can go in this direction, but you cannot go back. So after this goal, you can satisfy this goal, but you cannot go back. So when you satisfy this with Yozo-Eisman, you are here after this cut. When you try to go back, this is not permitted. And there are no other solutions, and PROLOG will say, no, I don't have any other solution to offer. So if you have that rule is ABC cut DCE, you can backtrack because between ABC. When you go over this cut in the area DEF, you can backtrack here, but you will never be allowed to go from D to C. You cannot go over this cut. And therefore, the first satisfaction of ABC will be the only one that is available. So you satisfy ABC and then go to DEF and satisfy that, but don't go back. This can be written as a diode that you have after ABC that permits you going only in one direction, or in elementary school, you go and say, you know what, you have here two-way street. You go back and forth in this street. And then you have cut, which is one way. You can go only in this direction. That's what this cut is telling you. You can go here, and then again, you have two-way street. You can go back and forth, but you can never going from D to C, because this is going in opposite direction in this one-way street. So ABC is satisfied, cut is always satisfied. You go in this direction, but if you want to backtrack, there is no backtracking over cut. Cut is a fence that is permitting you to go in one direction and not in the other direction. And this is something that is fundamentally necessary for study of PROLOG, and it is a procedural component, but permits you to create fast programs and to eliminate some permutations of solutions that are wasting time and giving you no information. So that's all for today. And we are going to start from this slide next time on Wednesday. Is there any question that I could answer?